All right, so last time we talked about different models for stress strain curves for soils. And the one thing we didn't get to was Janbu's tangent modulus. So I want to pick that up, tangent modulus method, which is, and I had you read part of his 1998. I think he actually wrote that document that I gave you in 1998 was published by the, see, it's not NGI, it wasn't the Norwegian, it was the, I forgot who published it now. Anyway, it was sort of a treatise of a bunch of stuff that he'd been putting together for decades. So the original publication of this stuff is much older than that. So this is like a lot over in 1998. That's just when he put together that big report that's published by that university. So, but it's a really good place. By the way, I found an error in one of the equations. I should post that up for you. At least I'm pretty sure it's an error. Anyway, so we're going to cover that method. And when we're done with that, then we're going to talk about how we can apply these elastic methods to do some simple stuff that we do every day, which is like stress distribution. So when you're done with this one, these you can go through these learning objectives. They basically say that you'll be able to use Yambu's method. All right, so let's talk a little bit about the motivation for that. So when we have a nonlinear stress strain curve, then if we want to calculate the strain, we actually have to integrate yeah, good. You know, we actually have to integrate this equation. We can't just use a linear equation because the modulus is changing as we move down the stress strain curve. And if I want to plot that in MV space, because this is actually strain as a function of stress, then we're going to have to integrate. You know, if we started off at some stress here, if this was sigma prime 0, and we're going to, you know, we're going to load out to this point here, which is going to be sigma prime final, then obviously, you know, I'm going to have to integrate the slope of this curve. Remember, the slope of this curve is little m sub v. I'm obviously going to have to integrate that from that stress to this stress in order to get this strain between those two. I can't just use a constant function. So before the days of PCs and spreadsheets, that was an issue because these are nonlinear functions. How are we going to integrate them? Now I could always use a piecewise linear model, obviously, if I wanted to. I mean, I could make this thing, let's see, it's not a good color. I think yellow will show up for that one. You know, I could make this thing linear piece by piece, right? And then this equation would turn into a simple sum. But that's still tedious to do, particularly in the days of slide rules and, well, I guess we had calculators back then. So what Janbu did was look at, he was looking for a simpler way. He was recognized that the stress strain curves aren't linear, number one. He also recognized that they're not even linear in log spaces we went through last time. So he was looking for a way, a simple way, and obviously the right way to do this is integrate the tangent modulus over the stresses, and that's going to give you the strain. But he was looking for a nice, simple way to do that in a way that captured the behavior of soils that he saw. So when he looked at soils, he saw what he called the 4 characteristic relationships, and these figures come straight from Yambu's paper that I assigned to you. And one is, if you looked at clays, and if you drew a line down here where the pre-consolidation stress is, he noted that, now these are all in arithmetic space. Notice this is not the log of stress, this is just stress. So these are all strain versus stress. So these are the compressibility curves rather than the stress strain curves. You notice that below sigma prime c, this is quite linear through that section. Then afterwards, you know, it becomes, as we talked about before, it becomes strain hardening, and it's curvilinear. Then if you looked at sands, you notice for sands that, again, past the pre-consolidation stress, the material was strain hardening. Before the pre-consolidation stress, it depended whether it was, he called them age sands, or you could call them over-consolidated sands. If they were overconsolidated, they were fairly linear, and if they were fairly young sands, that they were strain hardening even in that area. And if you look at rock, it's linear in both below the pre-consolidation stress and above the pre-consolidation stress. And finally, if you look at the quick clays, just as we showed before, even in linear space, it's significantly strain softening at this point, and then eventually becomes strain hardening again. So then he plotted the modulus as a function of the stress now. So all we're doing is plotting the modulus. So for the clays, when the clays are overconsolidated, you basically have a constant modulus. It's flat, right? And then in the places where you're on the virgin curve or it's normally consolidated, you saw that you basically had a linear relationship between the stress and the modulus. And for sands, when they're normally consolidated, again, he saw pretty much a linear relationship, although it does the gain in modulus does tend to decrease eventually. And we saw this when we plotted the stress strain curves for sands when they got the really high ones that gets really steep and the modulus doesn't really change much. And then below that, it depends on whether he's calling a young sand or an old sand. And that has there's some interesting papers on the aging of sand and how the behaviors of it change. It sort of becomes overconsolidated as it gets aged. And then for rock, our modulus is constant below this pre-consolidation stress, and then he has it linear increasing afterwards. And this really depends on the type of rock. Sometimes it's constant, and we're not going to talk a lot about rock anyway. And then for quick clays, you have this big drop in modulus as you go from as you cross this pre-consolidation stress. And then again, they start off rather linear. There is some strain hardening here, but it is strain hardening, and the slope of the modulus is pretty close to linear through that region. Although it's getting stiffer faster as you go up, as opposed to the sand, which gets less stiff. So this one tends to curve up in this direction a little bit, and this one tends to curve down that direction a little bit. So those are plots, again, of modulus versus the stress level. So either because he knew a good mathematician or he was a good mathematician, I don't know which it was, Yambu realized that you could model all those with a single equation, where the modulus is equal to the tangent modulus is going to be equal to, we're going to use some reference stress as our to take care of our units. And the reference stress is just 1 atmosphere. So if you want it in kPa, you put in, what's the number now, 17, is that right? No, I can't remember. But if you want it in kPa, you're going to put in one atmosphere into kPa. So that's where you're going to get your units from. And then sigma prime is our effective stress, and that's obviously going to be the units of that are going to come from the reference stress. And then this m is a modulus number. So this is going to be what you use to adjust your stiffness. And then the alpha exponent here is going to tell you how nonlinear this function is as a function of stress level. Remember, if we go back to here, so for the overconsolidated clays and for the rock, this is this is constant, right? The modulus as a function of stress is constant. So for those materials, what's alpha going to be if the modulus is constant for all stress? 0. No, not 0. 1, because you want the exponent to be 0, right? Yeah, because you want this whole thing to go to 0, and then this is just going to equal m times sigma ref. Well, this is a constant, and this is whatever the stiffness of your material is, right? All right. So and these equations and this derivation is in your textbook. So if you substitute this equation back into the integral to get the strain, you get this really, and then you solve it for the indefinite integrals, you get a very, very simple formula for the strain now as a function of the modulus number, the modulus exponent, and then just whatever your starting stress and your starting stress and then your ending stress are. So now we don't have to. So it's a really simple integral, right? So if you put this in the form of this exponential form and then go ahead and solve do the calculus, you get this really simple formula for the strain as a function of the starting stress, the final stress, and then these two parameters. So let's go back and look at that just real quick. So we were saying the problem with this nonlinear stress strain curve is I got to do this integral, right? And this, I've got to do this integral, and well, who knows what that can be? Well, if I assume that this curve always has the form, always has this form, then this is the solution to that integral. It's a closed form. It's pretty simple, right? Because I can do that. That's just algebra. Are y'all following me right now? Okay. So that's essentially what Yambu did. So he said, look, we know the stress strain curves are nonlinear. Really, the only reason we're using this C sub C and C sub R crap is because we're too lazy to actually do the integral. Let's actually do this problem right, because we know that C sub C and C sub R thing obviously doesn't work for all soils. We can just see that. So let's come up with a better way to do this. And so that's all he's done. But he still assumed this model right here for the modulus as a function of the stress. Okay, well, what happens when you do this? Well, if you do this, remember for over-consolidated clays and rocks, that was the case where the modulus was constant, right? Okay, so and for those, what do you get? Well, you have this formula for the strain equation, so that's this formula right here, right? And we know that has to be equal to delta sigma divided by the modulus because it's constant, right? I mean, the modulus is fixed, and the strain is just going to be the change in stress divided by the modulus. So in that case, the relationship between the modulus number, don't get this confused with M sub V, by the way. The relationship between the modulus number and the modulus is just that the modulus is just the modulus number times the reference stress, times 1 atmosphere. And we have a linear elastic material, right? Okay, so what's the other case where we're very familiar with? The other case we're very familiar with are the normally consolidated clays, right? And those are the ones where C sub C was constant, right? They were linear in semi-log space. Well, that equation, in that equation, alpha is equal to 0, and it reduces to this equation. So let's look at that one real quick. So that says that the strain using Janbu's parameters is going to be 1 over m times the natural log of sigma final minus sigma 0. Well, that looks familiar. What does that look a lot like? That looks a lot like our C sub C equation for normally consolidated soils, right? And in fact, that's got to be equal to C sub C over 1 plus E naught times the log base 10, right, of sigma prime final over sigma prime 0, right? So this is nice that, and for sure this is not a accident. I mean, sure, Janbu set this thing up to work this way. And if we follow that through, then if you remember the relationships between natural logs and log base 10, you could just show that the relationship between m and C sub C is this. It's just that m is equal to 2.30. The 2.303 is a conversion from natural log to log base 10. And then remember the 1 plus E naught over C sub C was the strain, right? So this is good. So Janbu's method, simplifies for the two cases that we're very familiar. For the case where it's there's a linear elastic material, at least on loading, I didn't say elastic, it's a linear material. Maybe elastic plastic, it's going to have plastic strain, but at least the loading curve is linear. Then we get a constant modulus, and it just has this value of the modulus number times sigma reference. In the case where we've got a normally consolidated soil where we know it's linear in semi-log space, we get the same form of the equation here, and that simplifies down to where the modulus number is equal. The relationship of C sub C to modulus number is right there. Okay. So what are the other two? Well, this is the normally consolidated sands or silts. What's happening with the normally consolidated sands and silts? Remember, they're strain hardening. As we load them, they just get stiffer and stiffer and stiffer. So in that case, Janbu looked at a bunch of data and said it looks like alpha is equal to about 0.5 for those. In that case, let's see, let me clean this up. In that case, we have this equation for the strain as a function of the stress. Here's our initial stress, and here's our final stress. In the case for the quick clays, we have this equation because now we've got a negative exponent there. So what he's done is get a very simple closed form solution for the strain as a function of stress for these different behavior types. And he lists 4 different ones. And if you read in Holtz, Kovacs, and Sheehan, it looks like this for the quick clays. Maybe this number is okay for the Norwegian quick clays, but for the Canadian quick clays, that number should be minus 0.6 or 0.7. And so these alpha numbers are determined in Janbu's method, are determined by the material type and whether it's over-consolidated or normally consolidated. So then all you have to do, if you can assume the correct alpha, all you have to do is figure out what the modulus number is, and you can fit that from your consolidation data just like you determine C sub C. In fact, for the case of normally consolidated ones, all you got to do is take C sub C divided by 1 plus E naught, multiply by 2.3, and that's the modulus number. So all we've done is take this equation, which was complicated because we had to integrate it, and we've replaced it with a really simple equation. We replace it with this really simple equation here. We replace it with this equation right here. And the alpha is actually going to be a function of soil type. And so it's kind of fixed once we decide what it is. If it's normally consolidated clay, right, alpha is going to be 1. If it's an over-consolidated clay or a rock, alpha is going to be equal to 0, which covers most of the important cases. And if it's a sand, alpha is going to be equal to 0.5. So we don't have to estimate alpha or compute alpha. We're going to assume that it has one of those values. And then all we have to do is determine what the modulus number is, and we can fit that from our consolidation data. So now this problem is problem of calculating the strain for nonlinear material is much more tractable, right? So now this problem is much more tractable because I've got this really simple closed form solution for that integral. Okay. Are you with me so far? Any questions about that?
I have one question.
Yeah.
That equation for the modulus, is that only for the case on normally consolidated clays, or is that applicable for all 4 situations?
This equation right here?
No, on the following slide. The modulus equation, is that applicable for all 4 types, or was that just in respect to normally consolidated clay?
So this equation, this one right here?
The third.
Oh, sorry, this one right here.
Yes.
So this is applicable for any soil for any normally consolidated clay, right? Because this is the same as, remember, this is the same as, I mean, it's the equivalent of this. So that's good for any normally any clay soil on the virgin curve. Okay? For sands on the virgin curve, they're strain softening, right? So now we don't want this exponent. If they're going to be strain softening, we don't want this exponent here. We don't want this exponent, the total exponent, to be 0 because we want it to be a function of the normal stress. Because remember, let's see if I can bring this up real quick. Let me think about this for a second. I want to try and figure out the easiest way to do this. Remember, for sands, this is what we had in stress strain space, that these things just get really stiff all the time. So obviously the modulus is a function of the stress level, right? So for those, we don't want that total exponent to be 0 because we want it to have some positive value. And so Yambu just fit a bunch of these and says, well, when that modulus is about 1, it's -5. Let me go back to the. So when that modulus is about 0.5, it seems to fit those. When the total exponent is 0.5, right? He has that the alpha is equal to 0.5. Well, that makes this total exponent 1 minus 0.5 is 0.5. So when this exponent was 0.5, that seemed to fit. Let's see, how do I get back to that other one? Well, the only one I know to do is do this. That seemed to fit these data. Does that make sense? Okay. Maybe I can do this from here. Nothing quite replaces the keyboard. Where am I at? Okay. So are we good here? Yeah? Okay. All right, so this is just a table out of Holtz and Kovacs. And so this is just for, the important part of this part, I guess, is this part, where what you're going to do if you use this method, you're going to assume alpha based on whether the material is a rock, or well, what you should do is look at the stress strain curve, right? We already talked about plot the linear stress strain curve, and if it looks linear in that region, then you can use an alpha of 1, which means you just kind of a constant modulus. In fact, you don't even use Yambu's method. You just calculate the constant modulus right off your data, right? If the material is a sand and it's strain hardening or a silt, then what you can do is assume the modulus, the alpha is equal to 0.5, which means the total exponent is equal to 0.5, and then fit that data to your consolidation data until you just pick your modulus number until it fits your curve well, and then that's the model you can use for Janbu's method. Now he gives some ranges for various soils here, but what you want to do obviously is go calculate these numbers for yourself. And in the case where you're dealing with something that's normally consolidated, then you're just going to pick you're going to pick 0 for that value, and then you're just fitting C sub C the way you always fit it, except if you want to use a modulus number, it's going to be a slightly different value. It's going to be 2.303 divided by 1 over the 1 plus E naught. Okay? So what's good and bad about Yambu's method? Well, it provides you this very simple closed form solution for calculating a nonlinear stress strain curve for both under strain hardening and strain softening and linear materials. Well, you just have to pick the right exponent. You have to pick the right alpha, and then you just fit your modulus number to it, and away you go. So it's simple. It devolves itself down into our traditional E log P for normally consolidated soils. That's good because we use that a lot, and it still seems to work. And the parameters you can measure just like you do off of any other stress strain curve. You have to assume the alpha. I will say you have to assume the alpha. I mean, you could do a parametric fit of the. I mean, you could do an analysis of variance and try and fit both alpha and M at the same time, but you pretty much assume alpha based on whether it's normally consolidated, whether you want a linear one, or whether it's a sand material, and then you only have the one parameter to worry about. Problems with it? Well, it only models one behavior. Remember for instance, the quick clays, we saw this really dramatic decrease in modulus, but then it starts to increase again as the stress level goes higher. Well, this can only model one of those behaviors. It can't model a strain softening followed by a strain hardening. So it couldn't really model a over consolidated soil that actually then went into normal consolidated mode because it only models one of those. Although you could break that material up into two pieces just like we do anyway, and model one of it with one alpha. You could model the linear part of it, the over consolidated part with an alpha equal to 1. And then when you get to the pre-consolidation stress, you could model it with an alpha equal to 0, and you'd have you'd have the same bilinear equation that we have for over-consolidated soils right now. The other big problem is just not commonly used, so a lot of people don't know about it. I don't know of anybody uses it in practice. I know plenty of people in practice that just take over-consolidated soils as having a constant modulus and go and calculate the modulus, and they forget. Usually they'll say they're calculating N sub V, and they just forget all the E log P equations and just treat it as a constant material. That's very, very common.
Is the reason for that one that you're not assuming anything and you are just calculating with some? What's the reason? The way you say it, I've never seen anybody using this.
Well, I think people don't use it for two reasons. One is because a lot of people don't recognize that the E log P method really isn't that good for a lot of stuff, right? I mean, we looked at a lot of those. There's a lot of places where you look at the E log P curve, you think you got this sigma prime C, and you had a constant modulus, right? I mean, if you just plot, you go home and just plot yourself, just take a line, and then plot it in semi-log space. It'll turn right over, right? I mean, just take a line, just take this thing in linear space and plot it in semi-log space, and it'll do this. That's just a logarithm. And if I told you that was the soil, you'd be right away, you'd be going, divide by 2, this is sigma prime C, this is C sub R, this is C sub R, right, this is C sub C, cool, and it wasn't. It was linear all along, you just didn't look at it. I mean, there's still a lot of people doing that, right? And the other reason I think is because, well, you can always just go and do a piecewise linear curve, and with a spreadsheet today, so what's so hard about doing that? That's not that hard, right? Whereas back when, in 1983, when I was in graduate school, you know, a spreadsheet was something that the accountants did down at the administration office, you know, and it was a big piece of paper with numbers handwritten on it. So these closed form solutions were really nice then. So, but people do use the straight linear curve where this is just going to be, you know, this is just going to be m or m sub v, depending which way whether you plot it stress versus strain or strain versus stress. People do that all the time, yeah. So if you want to say that's Janbu's method, well, it's one end of Janbu's method, right? But this concept, I mean, it's a uniform over all those different soil behavior types. All right. So that's Janbu's method. Any questions about that?
So, is the point of this method to try to give the soil that you're working on some kind of modulus parameters so that we can measure the settlement?
Yeah. So if you want to calculate settlement, and we haven't got to settlement calculations yet, but okay, why can't I? You know, we were last time we looked at this material, right? We said, let's see, let me find a good place to start this one. You know, we said, well, we have stress strain curves that look like this, right? When we plot them in linear space, they don't look, you know, they don't have a constant, you know, they definitely don't have a, they may have a constant C sub C in this space, but they're definitely not linear here. And that this, you know, we also said that this point where it looks like there's a dramatic change in modulus here, really there's not any significant change in modulus. So this, you know, this settlement is equal to 1 over 1 plus E naught times C sub R times the log of, what's that, sigma prime C over sigma prime 0 plus C sub C times the log of sigma prime final divided by sigma prime C, right? We all learned that one, right? Well, in this case, we said, well, C sub C seems pretty constant, and if we're looking at Bay mud and we're only looking at the normally consolidated part of it, well, that might work, but you know, back in here, that maybe not be a good model. And we looked at this model, right, where we said, well, if I did that, if I went to that whole equation here, you know, I'd end up with something that looks like this, you know, and when in fact, if I just plot it in arithmetic space, it's constant. Why would I go through all that trouble? In this case, the settlement is just going to be equal to m sub v times delta sigma times times L0. That's supposed to be. You know, times the original, you know, times, usually you write it as h, the thickness of the layer, right? Okay, well, and then we looked at sands that are like this, and we said, well, that ain't linear, and that ain't linear, what I'm going to do? Well, now I can write this as the strain is equal to, let me see if I can get this right, m times sigma reference times, I'm going to have to go to the other one because this one I don't have memorized. Alt tab. I can write this one, you know, I can write this as the strain, right? So then the settlement's just going to be equal to the height, the original height, times 2 over m times the square root of sigma prime final over sigma prime reference minus the square root of sigma prime 0 over sigma prime reference. Right? That's a whole lot easier than trying to do the integral. So now if you want to think about it, I have 3 different, if we're skipping quick clays for the minute, I have 3 different settlement equations. If it's a strain softening, I'm sorry, if it's a strain hardening sand, I can use this one. And I can find these parameters too. It's not like some crazy parameter I can't measure. I can fit that parameter off this stress strain curve, right? If it's a oops, going the wrong way. If it's a linear material, I'm just going to use this, right? And if it's a normally consolidated clay, I'll go back and I'll just use this part of the curve, right? Does that make sense now? So Yambu just kind of puts all those behaviors in one simple form that's just exponential form. So Yambu just uses this really simple exponential form for that's interesting. Didn't I tell you to erase all the ink? Yeah, I don't know why some of it's erasing or not. It's probably confused because I've gone back and forth too many times. Sorry, this is the one I meant to go to. This one simple form, right? So this equation, this equation and this solution to the integral encompass all those behaviors. You just got to pick the alpha. Okay? Yes? No? More? So now go back and read Yambu, see if you really understand it.